Welcome back, everybody, to another episode with Meti, with a fantastic researcher. Today, we have two amazing researchers, Daniel and Aditya, who are going to present for us CrossQ, which is a top 5% spotlight at the coming iClear conference. So, Daniel, off to you.
Well, thank you very much for the nice introduction, Haitham, and also thanks for the invitation. Um, Today, Aditya and I want to present joint work, which is going to be at iClear 2024. It's called CrossQ, Batch Normalization and Deep Reinforcement Learning for Greater Sample Efficiency and Simplicity. All right, let's jump right into it. So what we want to show you in this presentation is that you can accelerate deep reinforcement learning methods with old tricks as from regular deep learning. And more specifically, what we do is we take an off-policy actor-critic method like SAC, we delete the target networks, and we add batch normalization. And then what we end up with is state-of-the-art sample efficiency at vastly reduced computational cost. And you can already see that on the right-hand side. These are aggregated performances over 6 MuJoCo environments. On the top, you see the sample efficiency where CrossQ outperforms the current state-of-the-art baselines. And on the bottom, you can see the computational efficiency, which is where CrossQ really shines.
So, Daniel, sorry.
Yes?
Just a question. So on the x-axis, you're drawing percentage of environment steps, right? So
yes.
What is the total number of environment steps?
So that is a 300K environment step. So it is basically what the baselines used. And then on the y-axis, we have the IQM normalized returns. But we're going to get more into detail, this like more as an overview of kind of what you're going to expect.
Okay.
All right, cool. Right, so for the purpose of this talk, let's back it up a little bit and quickly introduce the reinforcement learning problem. And here we have an agent interacting with an environment by sending actions A to this environment, and then in return, it gets a new state and the reward from this environment. And the goal of this agent is to maximize the cumulative discounted reward, which it gets by interacting with the environment. And the idea is kind of to learn a policy which maximizes this, and this is depicted in this loop on the right hand side, which is the update loop. So what is very important and what a lot of research focuses on is to increase the sample efficiency of these methods, because usually these methods need a lot of those interactions with the environment. And especially in the case where we don't just have any simulated environment, but we have, for example, a real robot that needs to interact with the physical environment, samples are really expensive. And that is both because the real environment works in real time, so it is kind of slow to generate these samples. And on the other hand, for example, we also have problems like the hardware wears down over time, and we just cannot afford to have millions and millions of interactions. But one thing that is probably equally important is the time spent over here on this right-hand side, which is kind of the update procedure. If we're on a real system, for example, we also might have real-time constraints, and we just don't have time to wait forever for SGD to give us our new policy. And we will refer to this as the computational efficiency of such an algorithm. And we might measure this, for example, in wall clock time or the number of gradient steps an algorithm is doing. One important definition that we're going to need in the rest of this talk is the update to data ratio, which is simply the ratio between the number of updates you do per environment step. All right, and that brings us actually right next to the next slide, so which is about the question, what does current state of the art do? And it is, they really increase these update to data ratios to have very high update to data ratios. And there's a number of examples. So classically, we have model-based policy optimization as a model-based algorithm where you train a model and then you generate synthetic data so you can do more policy updates per real environment interactions. And then more recently, on the model-free side, we have algorithms like RedQ, DrawQ, or SEC with resets, which do higher update to data ratios and take different measures to be able to do so. And arguably, high UTDs are great in the sense that they boost sample efficiency, but they definitely come at the cost of very high computational cost. And they add, or usually add, the problem of more algorithmic complexity. So you need, for example, regularization tricks in the case of RedQ and DrawQ. You need to account for the Q function bias, and that just makes the overall algorithm more complicated. So the question that we want to ask is, could we accelerate the training itself instead of just training more, to be, in a sense, more like the soft actor critic, which uses a low update to data ratio. So it does one environment interaction and then one training update. All right. And to tell you more about that, we're actually going to quickly switch to Aditya. In case you have any questions about this, you can ask this while we switch. So.
Okay. So in case nobody has any questions, I'm going to proceed. All right. So as Daniel said, we want to now look into really accelerating training instead. So instead of specifically trying to understand, Q bias mitigation and such things, we are going to look into ideas from deep learning, architectural ideas. Because we actually are aware of some of these things, and that specifically here is going to be batch normalization. So batch norm is pretty old by now, for some sense of old. It came out in 2015, and they found that if you use batch norm in your deep networks, like just stuff it between your layers, then you're going to be able to descend the loss landscape really fast. It accelerates training. You can get to the same low losses an order of magnitude faster. And why batch norm helps in this way, it's still a bit of a mystery. There's been many papers about it, and nothing's very conclusive yet. But the general idea is that it improves the conditioning of your network, and this will somehow let you use bigger learning rates and just make the gradients flow better. So what is batch norm exactly? Let's unpack this. So let's say that you got some neural network. You got some layers. Let's say they are fully connected layers. Could be anything really, but let's say they're FC layers, and you have some nonlinearities on top of them. So you can augment this network by stuffing in these batch norm layers. So now let's blow this up. What's inside one of these batch norm layers? So the way this layer works is you got an incoming batch of samples. So these samples are feature vectors, one for every data point. And let's say that this feature vector has a bunch of different entries inside of it, like red, green, blue, and purple. Now, these entries inside the feature vectors can be differently distributed. Like some can have very high variances, and some can be pretty narrow and peaked, and they have different average values. They're differently distributed, being the point. And the batch norm authors argue that these different diverse distributions and also the way they change.
Quick question. In this picture, each column corresponds to the data point, yeah?
Each column is one data point. Yes, that's a feature vector.
Mm-hmm. Yeah, I got you.
Yep. Right. So you send in these batches of data points, which are these different feature distributions. And what batch norm does is it estimates the batch moments. So it's going to estimate the empirical mean of the batch, and it's going to subtract that from these samples. Then it's going to divide it by the estimated standard deviation. And then it's going to do two quick operations, which are, oh, by the way, so upon doing this, the expectation is that you somewhat standardize your data. Of course, like your data is not really Gaussian distributed, but if it were Gaussian distributed, then the result of this transformation would be that you get something resembling a unit Gaussian. In any case, this is a very nice data pre-processing step in pretty much any regression pipeline. So Batchnorm just bakes it in. And then you've got these two extra learned parameter vectors. So these are not like dense layers. These are just like flat single vectors that you element-wise multiply and then add. This is to restore the representational capacity of Batchnorm, because if you very aggressively standardize your data like this, it somehow kills the diversity of functions you can learn. So that's why they include these two extra vectors. So that's the learnable scale and shift. And once you apply these transformations, you get the so-called normalized vectors. Of course, it's not really normalized, right? They're actually denormalized afterwards in a more controlled manner with gamma and beta, but that's what they call them. Important caveat to remember. When you're doing inference, you don't necessarily have a batch to feed into your network. You probably have single data points. Or you could have differently sized batches, depending on what you want to do. So then you don't actually use the batch estimates of these mean and variances. You instead use a running average that you've been silently computing during test time to standardize your data. Sorry, you've been computing it at training time and you use it at test time. So that's how Batchnorm works. But now we would like to use Batchnorm in DeepRL, specifically in off-policy TD, which is where the most benefits of sample efficiency gains lie. But there are some issues. And we're not the first ones to have had this idea. But it turns out that the internet is littered with the graves of Batchnorm in DeepRL implementations. People have found that it just doesn't work. Usually when people insert Batchnorm in like your Q functions, they find that it simply fails to train, or the Q networks diverge, like the Q values just blow up to infinity or something like this. And by now, in all these years, the general recommendation or wisdom is that don't use Batchnorm if you can avoid it. In fact, it never has seemed to work, so people always avoid it. Let's now try and understand why it doesn't seem to work for people. So what happens in TD learning? You sample some off-policy transitions from your replay buffer. You sample them in batches, right? So you've got states, the actions you took at those states historically, the rewards that you got in those transitions, and the next states that you got right after. And then you would take your currently trained policy, whatever iterate you have during the agent training process, and you sample actions for the next states according to that policy. So your sampled batch is off policy data, but your sampled actions are according to your current policy. And now you're going to do two forward passes. First, you're going to feed S, A into your Q network. You're going to generate Q predictions. Then you're going to generate Q predictions for the next time steps pair of S, A. And finally, you're going to compute the TD loss, which is this, and where gamma is the discount factor. Now, this is probably the standard implementation that most of these actor-critic training methods have. The actor training step is separate, but we don't show that here. It's not so relevant. But there's something here that can really cause issues for Batchnorm. And in this paper, we identify that. So if you look closely at the two forward passes, you'll see that the state batches, they have to be identically distributed, right? It doesn't matter what ST and ST plus 1 exactly are. The point is that they're just pretty much the same set, just offset by one time step. And they have the same distribution. You can verify this empirically, of course. But what's different is this. These guys, they have different distributions because AT comes from your replay buffer, but AT plus 1 comes from your currently trained policy. So these batches have different statistics. And we can look at this empirically. So here's an agent that was trained over many, many time steps, the standard training length that we have in this paper. And we're going to take snapshots of the action distributions over time. And on the y-axis, you see one coordinate of your action space. And on the x-axis, it's another coordinate. These are just like arbitrarily sampled dimensions of your action space just to get some 2D plot. And you see that the distribution of actions from your replay buffer is very different. That's blue. It's very different from the actions that your policy wants to propose. And it's persistently different throughout the process of training. And this can be lethal for batch norm. So you can imagine that when you do the first forward pass, it's going to compute some batch statistics. And then when you do the second forward pass, it's going to take the blue batch statistics and try to normalize the red batch with those statistics. And because all of the features in the intermediate layers of your Q function are kind of influenced by AT+1, those are also going to be wrongly normalized. And this is a huge problem.
Aditya, may I ask a quick question?
Yeah.
You said that with the states, this ST and ST+1, they are identically distributed. But why? If we know that ST+1 distribution it depends on ST and AT, why can we say that they are identically distributed?
Yeah, that's a good question. So if you got a very, very tiny episode length, let's say you got just 2 time steps, then of course the starts and the ends have to be differently distributed, right? So in that case, they're going to be different. But in practice, for the kinds of problems that we care about here, like these continuous control problems with like 1,000 length episodes, right? There, you just arbitrarily sample any ST, and then the next state is ST+1. And also, at the next time step, you're gonna commit ST+1, and then whatever actions there are, and then ST+2 to the replay buffer. So in this sense, they're almost identically distributed. Sure, the start state distribution can be slightly different for all of your episodes, but like afterwards, they need to be nearly the same.
I see. Gotcha. Thank you.
All right. So as I said, these moments are different, and this
sorry,
is a huge...
Aditya, sorry to interrupt, but can you repeat the explanation again? I still don't think I understood that about the independent distribution.
About S?
Yeah, S and ST+1.
Okay, so let's say you got a very, very long episode, and all your episodes are pretty long. Then in this limit, the way you commit transitions, this S, A, S prime transitions to your replay buffer, is that you're going to take every time step, you're going to commit that transition to your replay buffer, and then you're going to move on to the next time step, like as the agent acts, and then you're going to commit that transition to your replay buffer. So everything that you committed into ST in your replay buffer is also going to be committed into ST+1, except for the very, very first time step in your, let's say, 1,000 length episode.
I see. Okay. I think I understand a bit more. Yeah, cool.
Yeah, okay, great. Right. And this is why we regard them as being nearly identical. And if you actually plot out these distributions for them, they do look identical. Like it's barely a rounding error. So we have, so by the way, this is a problem, and we see that everybody who tried to use batch norm in whatever implementations that we saw online seemed to not be aware of this distinction, that the fact that these A batches have different distributions. So they're using batch norm wrong. So we now need a way to correct it, which is what we do. It turns out that this fix is just absurdly simple. So look, on the left here, you have these 2 forward passes, and then you generate the loss, right? So the tweak that we suggest is the following. Just concatenate the ST and ST+1 batches and the action batches together into one big batch, like double-sized batch, and just send it through your Q network in a single forward pass. And then split the output of this big batch back into Qt and Qt plus 1 over here. So why do we do this? We do this because now, from the perspective, the point of view of the batch norm layers in your network, all the inputs, like every element of a batch that it sees, belongs to one unified mixture distribution that contains samples both from AT and the AT prime, AT plus 1 batch. And when you have this kind of a wider mixture distribution, you're going to use consistent moments that are going to, at least the means are going to look like the arithmetic mean of the two means of both batches. And we use this mixed mean, these mixed normalization moments, and therefore there's never a mismatch now. And by the way, we find that this works very effectively. This was a very, very simple hack.
And do you know if I will concatenate not just two consecutive but longer consecutive sequence, will that trick perform better?
In what case would you have a longer consecutive sequence of forward passes?
If, for example, I don't know that if you want to have some, if you want to take into account the longer effect of your actions, like a long horizon type of effect of your actions. I think in RL there's a special name for these actions where you kind of like take the effect, not just the immediate action, but like a sequence of actions.
Okay, I think you're referring to the end step returns, right?
Yeah.
Okay, so again, I think this this should depend very much on the precise way in which you do your Q predictions. There are many ways to do Q predictions. Like in DQN, for example, they don't even feed the actions in. They have different action heads. So I don't know like what exact way of predicting Q values you would do in a specific end step implementation. But if it were done in this manner, where you just feed in like S and A for a specific time step at the same time, then I would say that yes, if you're doing this for like 2 or 3 or 4 time steps, then absolutely you should concatenate them all together.
Gotcha. Thank you.
Yeah. Okay, so we find that this works surprisingly well. I mean, there's not much surprising about it. It's just we fixed the inconsistency of moments problem, and then it works. But there's something we just changed here that's more than just concatenation, and it's this. You see, in modern deep RL TD learning, we have something called a target network. It's a copy of your live Q network. So these parameters theta dot are gone now. We just have one Q network. So let's unpack this. What's going on here? So the target network is, you can think of it as a kind of slower time-varying copy or version of your live Q network. And this is here, tau is going to be something less than 1. So this is like a Polyak average, or a moving average, or a low-pass filter. And the way this has an effect on your TD learning is that you're going to use this slower Q network to predict your regression targets, your QT plus 1, which has the effect of somehow slowing down the bootstrapping, the credit assignment backwards in time that is characteristic of value-based methods in reinforcement learning. And this can be widely regarded as a nasty thing or a necessary evil, because like, why do you want to slow down your learning? And many have thought this. However, it's been really crucial for deep RL stability. In fact, ever since deep RL became really deep, which is 2015 in DQN, target networks have been a part of it. So target networks first came out with DQN, and the version of target networks they used was a periodic snapshot of your live network, every 5,000 steps or so, or probably more. And the year after came out DDPG, which is for continuous control. And that version used the Polyak average, the kind that we are showing on the left side here. But surprise, surprise, in this paper, we somehow find out, and there's more in the appendix if you want to see that, it turns out you don't need target networks. If you simply somehow use normalized activations or bounded activation functions. And guess what? Everybody is using ReLUs, unbounded activations, and it's blowing up for them without target nets. Just use bounded activations or use feature normalizers. And guess what? Batchnorm is a feature normalizer, and it also makes target networks unnecessary. So in conclusion, what we then do is to turn SAC into CrossQ, we make just 3 simple changes. First, we use Batchnorm. We just add Batchnorm in between all the layers, and we use it the right way or the safe way, the way we showed. And this just shows the same kind of sample efficiency boost as people see in supervised learning. We delete target nets. This simplifies the algorithm, and by the way, also makes it easier to use Batchnorm in your Q networks, because with target nets you have to worry about this extra running average of your parameters, and Batchnorm has its own running averages, and the combination of these two is just really complicated to even think about. And lastly, a super minor change. We just use wider layers in the Q network. This raises the performance ceiling that we can achieve. And now Daniel is going to show you some of the experimental results that we got, lots of plots and fun things. So if you have any questions, you can ask right away.
Yeah, yeah, this is very, very interesting, actually. So what you've done is you actually simplified the DeepRL problem back to, or DeepRL solution, right?
That's right.
Yeah. So is there any theoretical grounding behind those additional tricks that you've looked into? Like, because I noted that you were mentioning this Polyak averaging as a low-pass filter in a way, right? Is there a way we can connect, some of the theories from the two fields to try to understand this determinantal effect of, slowing down learning more than just by noticing it empirically, so to say?
So we actually have some extra experiments where we show that target nets actually do slow down learning, and we disentangle this slowing down effect from the presence of Batchnorm. And this is purely empirical. Theoretically, we don't have, I would say we have no clue why this works.
Yeah. No, I mean, but this is amazing stuff. Yeah, thank you. Yeah.
Mm-hmm.
And we also have a slide for this in a minute, I think.
Mm-hmm.
Yeah. All right. Can you guys see my screen?
Yes.
All right. Okay. One quick thing before we get to the experiments is, as Aditya mentioned, it makes the algorithm really simple. So here we actually just have a example of a very minimal JAX implementation of the critic loss. And I kind of want to quickly note the main changes. So basically here you now just have one single Q network. Just below that, you do the concatenated forward pass, as we've seen. It's also pretty easy. One thing you then need to do, of course, is split up the bet into the original batches again. And then you need to put a stop gradient on the next Q values, because of course, yeah, you want to use them as targets. And that's it. And the nice thing is you don't see all of the things that you can remove, namely the target networks and the Polyak averaging and so on. So yeah. All right. Without further ado, let's, oh, sorry. And it's not exclusive to SAC, but you can actually do this with TD3 or any other off-policy TD learning method.
And why JAX?
Why JAX? I just love JAX, to be honest. Yeah, I'm a fan. And it just, I don't know, we also had an implementation in PyTorch in the beginning when we were thinking about which framework we're going to do our experiments in, and we just had much faster runtimes for, well, across the board, of course, also for the baselines, but for everything. So it just was faster for us to do all of these experiments, which were quite a lot. As we're probably going to see in a sec, just overall here, because we evaluated everything on 10 seeds each to be as rigid as possible, and so on. And okay, here you basically on this slide see the sample efficiency. And I've hinted at this in the very first slide already with this aggregated curve. Here you see it in a per environment setting. And we can see that, again, CrossQ either matches or surpasses the current state of the art, which is DrawQ or RedQ. And that with only 5% of the gradient steps, because we don't have the high UTDs. It also translates to DM control environments, for example, and many more. And we do have DM control in our appendix. I didn't include them here in the slides, but just as a side note. And you can also see that we have a version of CrossQ based on TD3, just to really show the point which we always said. You can combine it with other methods as well, and we see the same kind of performance increases there, which is super nice. And if you again aggregate them in the bottom right, you see that also with this IQM norm return, which is statistically more valid than the individual curves, you see that we're nicely sitting above the baselines. All right, this becomes even more dramatic if we now plot this in terms of the computational efficiency. As we said, 5% of the gradient steps, which translates into roughly 4 times faster wall clock. Everything is jittered. So coming back to Jack, so that makes it nice. And one side note is we're also actually being very nice to the baselines, as if we would have taken the original RedQ implementation, they do all of the critic updates in a loop. So then we would have probably been 100 times faster, not just 4 times faster, because here we actually parallelize over all of the critic updates, so over the entire ensemble. All right, cool. One important thing that RedQ and DrawQ really look at is the Q bias of these methods. And the Q bias is basically the difference between what your Q function says and the empirical return you actually get from the environment. And the common wisdom from those papers being that it's important to reduce this Q function bias in order to improve the learning performance. Because if you just take like off-the-shelf vanilla soft actor-critic and you increase the update to data ratio, the Q function bias will usually just explode. And we've done those experiments. We've put CrossQ in there because we thought, well, maybe CrossQ implicitly also reduces the Q function bias. But in reality, as you can see in those plots, it's a little bit more complicated. On the left-hand side, we've just randomly picked 2 environments, and we have all of the other ones in the appendix as well. And you can kind of see RedQ has the lowest Q function bias. It's exactly doing what it's designed for, but CrossQ matches, in those examples here, matches the performance despite having a higher or sometimes even much higher Q function bias. So yeah, the story is not that clear in regards to this. Then the other thing that Aditya already hinted at kind of is the effect of disentangling the effect of target networks and the batch normalization that we add. And the question is really, how much does the target network slow down training? So what proportion of the speed up comes from removing the target network, and what proportion comes from actually adding the batch normalization in there? And we have a nice experimental setup where we use 10H activations, which are those bounded activations where we found that using those, we can actually already train without target networks. They permit us to train stably. And we have a little bit more details of that in the paper. But as we see, and this allows us to kind of run all of the combinations. So soft actor critic without target networks, then just with batch normalization, and then, as we say, the CrossQ style, where we remove target networks and add batch normalization. And there are not much surprises here. We see that removing target networks usually slightly helps, but it's not dramatic. Just using batch normalization, so keeping the target network in there and adding batch normalization, usually fails. And that is because of this distribution mismatch we talked about earlier. And we get the best results by using batch normalization without target networks. So here we really attribute the effect in getting those much better sample efficiency numbers to using batch norm in the correct way, which is accounting for this distribution mismatch. All right, and that already brings me to the conclusion. So we've seen that batch normalization can accelerate deep reinforcement learning quite drastically. And we've put all of this into one method, one algorithm. We call it CrossQ. It's essentially an off-policy TD method plus batch normalization and without the target networks. And what you get is state-of-the-art sample efficiency at really reduced computational cost compared to the current state-of-the-art. And as a bit of an outlook in future work, we now really want to go into the real world in real time on the real robot and do kind of this sort of, learning in the real world, where most of this motivation actually came from initially also. And something else that we want to also look at is, can we even scale this up even more and make it faster and go to, for example, larger tasks like visual RL tasks and the like. All right, and with that, I want to thank you, and I guess we can take some questions.
Thank you so much. This has been amazing. I mean, fantastic work, you guys.
Thank you.
Maybe I could start first by just some questions. So I know Jan would like to see this on the real robot, and I mean, your sample complexity is still kind of high, like e to the power 5 or e to the power 6 or something, right? And what do you think are the main gaps, to get this actually operational on a, real system?
So that's a good question. So it's something in the order of times e to the 5. Yeah. And we think that if you select the right kind of time discretization, this is probably going to be, I think with a very reasonable discretization, this should be about 15 to 20 minutes of learning time on a real robot. So if you place in the right safety guards, because methods like SAC love to trash your robot about, if you place in the right safety guards and construct the task well, I think you should be able to see interesting policies emerge within this time, and it depends entirely on the task, of course, right? But one of our methods that we compare against, DrawQ, one of the state-of-the-art methods, it's been tried out on learning quadruped locomotion from scratch in between 10 to 20 minutes by Sergey Levine's group, and they found that this works. Right. So, and as we showed, CrossQ appears to be comparable or faster than that in like less compute time. So we expect that this should be an okay thing to try out on real robots.
I see. Okay. Interesting. Yeah, I mean, amazing. And one other question. So have you guys assessed this on top of a model-based RL setup? Because I mean, like if we think about something like I don't know, a DynaQ, for example, or things related to that, wouldn't this even further boost your sample efficiency?
It's a great point. I mean, this is something which we're actually looking into right now. So no, we have not assessed this fully, but I mean, in a way, this kind of falls under the scaling up points, I would say, which I said for future work. Yeah. So yeah, we definitely have this in mind.
Yeah, that sounds amazing. Yeah, I mean, I also want to see if anybody in the team has any questions as well. Anyone has any questions from the team side?
Hey, thanks for the talk. I have a question regarding the, the statistics in the batch normalization. I was wondering, have you tried, instead of having one mixture for 80 and 80 plus 1, have you tried maintaining two different statistics, like one for 80, one for 80 plus 1? And do you think it would work?
So that's a good question. And we don't have this in the paper, of course, but we've tried exotic things like this. We've tried using, like, manually specifying different mixing coefficients for these two different distributions. And it seems that, yeah, as long as you keep it consistent, as long as you have exactly one combination and not this flip-flopping between the two, this works. This does help. Of course, that's going to require you to hand program the mixing yourself. The easiest way is to just send both things together in the same forward pass, in which case it's like 50-50 mix, and it's super easy for you.
Yes. But could you maintain two different statistics without mixing those?
Yeah, good question. So maintaining two different statistics would entail that you normalize the batch that comes with A and the batch that comes with A prime differently with their own specific statistics, right?
Yeah.
So I believe that, I mean, we could be wrong, but this does not seem theoretically very sound to me, because you got a network that perceives data that's distributed a certain way. And if you now normalize the incoming stuff differently, I believe that the predictions are going to be wrong. And this is this wrongness of predictions due to mismatched moments is exactly the thing that we implicate in this paper with regards to training stability. So I believe it would not work. But I mean, are there more interesting combinations or different ways to normalize that could be tried? Sure, I think that's an open question.
Yes. Thank you.
Mm-hmm.
Right. James, you have a question. I saw you unmuting yourself and then muting yourself. Do you have any questions you want to share?
No, sorry, I'm just having some computer problems.
Okay.
I thought it was a really interesting talk, though.
Okay, cool. No problem. Right. This sounds amazing. And one last part from me. So, well, actually, two more questions. One technical, one less technical. So, when you talk about going to vision-based RL, right, like doing vision-based control, is this method a plug and play, or do we need to add some more tricks to it?
Okay, that's a good question. I think it can be used in a plug and play manner, in the same way that people use soft actor critic in a plug and play manner with vision-based RL, right? You replace your MLP with a convnet, and then you see what happens. And batch norm has been shown to accelerate convnet training. That's actually the main class of networks in which it's been used. So we hope to see similar things happen there too. Yeah.
I see. Okay, cool. Right. So we're asking everybody who's coming to us, to give us feedback about their experience in the review process, right? Because we know that everybody is complaining about the review process, and what we would like to know is how was your experience with iClear in this case? How was the review process? Was it good, bad? Any ideas to improve it?
Okay, I think, and Aditya, you can also say something about that as well. From my experience, stressful as always, but I think we were kind of lucky in the sense that we had, we had a lot of questions, which helped us improve the paper over the review period. Also gave us a lot of work and a lot of arguing to do. But overall, it was nice to have a relatively responsive reviewers that also provided us with high quality reviews. I know that for some of our colleagues that also wasn't the case. So in that sense, we were happy that rather we had some work to do than just silence, basically.
Yeah. I would say that we had fairly thorough and responsive reviewers. So before the rebuttal period closed, and by the way, we were not very early in submitting the rebuttal. Before the rebuttal period closed, everybody, like all the reviewers, made sure to give us a response, which was really nice of them.
Awesome. Yeah. And is your method open sourced? Can we play with it? Is it somewhere we can use it, or you're planning to open source it? Or
we are working on it any day now. Hopefully in a couple of days.
Awesome. Yeah. All right. So this is a spotlight in iClear, right? That's what I understand. Yes. Awesome, guys. Okay. So with that, I want to thank you guys again, both Daniel and Aditya. This was fantastic work, and congrats again. And I'm looking forward to using your method. So thank you for coming, and wish you all the best in your iClear conference and so on. So thank all
you very
for
much.
following us, and
thank you,
we'll see you in the next episode. All right. Cheers.